In our previous video, we talked about how enzymes have a dual nature. Do you remember what that dual nature is? First of all, enzymes are specific. That is, they act on very particular substrates and they only speed up particular reactions. Second of all, they're catalytic. That is, they speed up reactions and they're unchanged by those reactions. Now, in the first case, the specificity, it's the active site that's responsible because the active site and the specific chemical, the substrate that it interacts with, complement each other chemically, much like a hand fitting inside a glove fits. Catalysis, or the catalytic nature of enzymes, is also carried out by the active site, but in a very different way. Now, in order to understand this, let's revisit a reaction that we talked about earlier. That is the breaking of a peptide bond, like this one right here, by chymotrypsin. And let's just remember that when we do that and add a water across it, we end up with a carboxylate and a protonated amine, like that. So, in order to understand how an enzyme speeds this reaction up, and this one, by the way, would be sped up by chymotrypsin. Remember, chymotrypsin breaks peptide bonds near or after phenylalanine, tyrosine, or arginine. So, in order to understand how this is going to speed the reaction up, we have to understand why it's so slow in the first place. Let's start with some reaction arrows and a description of how this reaction would occur if we were just going to put a peptide bond in water, in which it goes extremely slowly. In order for this to happen, water would have to attack this carbonyl. That's the first thing that would happen. And water is terrible at attacking. We would say it's a terrible nucleophile. It would be much better if it was an O- or an OH- hydroxide ion. The next thing that we have to say is that the double bond O would flip up and make an O-. That is going to be visualized down here below in what we call a reaction energy diagram. Let's orient ourselves on this a little bit. Over here, we have the substrate, which is the peptide bond that we're trying to attack, and we have the water. Those are actually both substrates. And over on the right-hand side, we have the product, which is now having that carboxylate and that NH3 that we talked about right there. Now, like I said, during the attack, the water has to lose a proton to become an OH to be a better nucleophile. And then, like we said earlier, the pair of electrons is going to flip up and you end up with a very different species right here at the peptide bond. The water OH has become connected to the carbon and the double bond is flipped up to be an O-. Now this is different in two ways compared to the substrate. Its shape is different and its charge is different. Let's pause the video for a moment and let's determine the shape and the charge of the substrate and compare that to the shape and the charge of the activated species up here. Pause for a moment and try that out and come back. All right, well, I hope you took a moment to try that out. Let's start with the charge because that's a little bit easier. Notice there's a peptide bond here and that's all neutral. Remember, amides like that are always going to be neutral. And so I'm going to put a 0 for 0 charge and put a circle on it. Up here, on the other hand, because we flipped that double bond out, we now have an O-, and that's a -1 charge. So there's a difference in charge. There's also a difference in shape. Down here we have standard carbonyl, and that's trigonal planar. So let's make a note of that. Trigonal planar. Up here, it's hard to see. It's not shown very well in 2 dimensions, but this carbon now has 4 groups around it. In fact, what that is going to be is tetrahedral. Okay, for both charge and shape, there's a difference between the substrate and what we see at the top of the hill here. And the tetrahedron and the negative charge are very unstable. And because they're very unstable, they have very high reaction energy. Okay, so let's move this over, or maybe zoom it out a little bit, and point out that the axis, the y-axis over here, is reaction energy. And the higher it is, the more unstable it is. So what we have over here is very unstable, whereas what we have over with the substrate, it's lower and it's more stable. The product is even more stable because it's even lower. Okay, that's helpful. In order for the substrate to get to product, it has to go through this very unstable mountain in the middle before it can get to the stable product. And this over here is what we call the transition state. Sometimes textbooks like to use a double dagger for that, and that's something you might have seen in general chemistry as well. So, we've defined this so far with the y-axis being energy. Let's just put on the x-axis down here, reaction progress. As we go from substrate to product, we must pass through the transition state. Okay, let's note something about the mountain that we have to get over here in the middle. That's very high. We call this the activation energy. And that's the activation energy in the absence of enzyme, minus enzyme. And let me say it again, because that's a high mountain to get over, it is a slow reaction. Now here's what enzymes do to make this go faster. Enzymes lower the mountain. They lower the activation energy, making it easier to get over the hump in the middle. So this is the activation energy, C, in the presence of enzyme. And so enzymes make it much easier, that is quicker, to go from substrate to product. Instead of having to come up over this big hill, it's much easier to flow over that. Now there's one more thing here. It's the difference between the substrate and the product. And let's just call that the reaction energy change from substrate to product. It doesn't really have anything to do with enzyme. Reaction energy change for the whole thing. Okay, let's go down to the bottom here and summarize what we say here. Enzyme speed is faster when the activation energy is lower. The second thing we can say is that reaction favorability, that is, whether this reaction is going to want to move forward or backwards, is dependent on the relative energies of substrate and product. Okay, let me put it this way. The reaction is favorable in the forward direction because it goes downhill from substrate to product. But it's slow in the forward direction because there's a big hump in the middle to get over. Enzyme makes it faster by lowering that. Here's a couple of questions for you to consider to finish this video up. Pause for a second and see if you can come up with the answer for these two questions. What effect does enzyme have on the favorability of the overall reaction? And number two, if an enzyme makes a reaction speed up in the forward direction, what does it do in the reverse direction? Pause, and then we'll go over those. Okay, let's zoom out a little bit. Remember, the dotted line there is the presence of the enzyme. What effect does the enzyme have on the overall favorability of the reaction? Remember, the overall favorability is the difference from here to here. And notice the enzyme doesn't change that. So the answer is nothing. The enzyme cannot make this reaction more favorable or less favorable in the forward direction. That's already determined by the difference between substrate and product right there. Okay, if an enzyme makes a forward reaction speed up, what does it do to the reverse reaction? This is a fun answer. Notice that the reaction goes faster in the forward direction because the hill is lower. Is that not true of the reverse direction as well? The enzyme is lower for the activation energy. So the answer, may be a little counterintuitive to you, is that it speeds up the reverse reaction as well. Okay, that's a complex conceptual understanding of how enzymes speed things up. We'll continue on the next video with a little more chemical definition of this subject.